Okay, thanks, Emily. And good morning, everybody. Thanks for being present. So today I'm trying to do some proposition about building more open medical data sets. So, okay, as mentioned by Emily, first slide presenting myself. So I'm a member of INRIA, working in Team Almana. Almana is a team which is specialized in natural language processing. And of course, these last few years, we have been involved in building and distributing large language model for French, for example, so with Camembert, and a biomedical version of Camembert, which is called Camembert Bio. And we have very recently distributed a suite of three models, three LLMs called Gapron, 1.5 billion, 8 billion, 24 billions. And Gapron is also a French cheese. But we have not yet a nice logo for these models. And so my research areas are in mostly parsing and grammars, but with interest in knowledge acquisition and information extraction. And I'm currently involved in several medical projects, including Oncolab, aiming to extract information from clinical reports for two kinds of cancers, and FG4H, about creation of a French medical LLM using a very large set of clinical data. Okay, so let's move to the core of this presentation. So about a collection of health data. So why building collection of health data? So there is several reasons for that. First, for example, for running medical studies, kinds of digital cohorts. So for that, we need small to medium scales of data. We may also want to explore statistical distribution, usually exploiting databases. But what interests us more today is about training machine learning models, for example, or even more large language models, LLMs. And for that, we have two phases, usually. First, pre-training LLMs, and for that, we need a very large amount of data, so large to very large scale. Or we may want to fine-tune LLM using some annotated data. And for that, we need a medium to large scale amount of data. And of course, it's not just about training. At some point, we need to evaluate these models. And for that, we need also some data, small to medium scales. So we already have today's several models, medical models or clinical models, such as FLAN-PALM, MedPalms, MedGEMA, Gator, Meditron, Clinical BERT, and so on. So this is something which is coming more and more today. And why we need these clinical models? Actually, there is a large range of potential applications for medical research, which is something I'm very interested in. So data analysis, for instance, but also to help professionals, so doctors, for taking decisions or to speed up some administrative tasks. Also for education of doctors. And something we should not forget is the use of LLMs for patients, and in particular to provide simpler explanation or more explanation to patients in a way that they can understand these explanations. So for example, to explain some result analysis. Okay. So what kind of data, medical data or health data, we have to deal with? Actually, a very large diversity of them. We can have health data in databases. So this is structured data. We can have data coming from examination results. We may have medical imagery, so different kinds of imagery. But I'm not going to talk more about these kinds of data today. What I'm more interested in is unstructured textual clinical reports, also called electronic health record, EHR. And so this is many kinds of clinical reports. As you can see on this distribution of kinds of documents we have collected for some experiment. We see that we have a large set of prescriptions, but we have also a large diversity of different kinds of clinical reports. But we also have some letters that we have to deal with. For example, patient-recorded letters. And we have this diversity of documents. style, but we also have diversity of these documents between different institutions. The way they are written or presented may differ largely from one institution to another one. For instance, we have an example of PDF document here, and I'm not going to talk too much about this part, but the first important step, of course, is to convert this PDF document to some textual representation we can work with. And that means to get something which is a clean textual representation with some structure, sections, the different components of the document. And so here you see some example provided by a tool we have been involved with called Grobid. And you provide some input PDF document and you get some XML TI clean structure representation with a different part of your document. But of course, there are many issues with such conversion. For example, you can deal with a scanned document, which is much more difficult to get a nice representation. Your document can include tables, you have abbreviations, and so on and so on. So very often you have to define or learn different templates for your different kinds of documents, which is maybe a difficult task and a lengthy task to do. Okay, as you may know, handling health data is quite delicate because you are dealing with very sensible data. So of course, we know that we have to take some basic safety, such as accreditation to access data, to store data on some secure infrastructure. For example, in France, you will need something which is called HDS certification. And when most of the time, your data should be kept in encrypted form. But actually, this is not sufficient from a legal point of view because you always have a risk of data leak, of data that could be used to have a use impact about people, about, for example, jobs, insurance, loans, and so on. We have to be very serious about safety of this health data. But you may wonder about not distributing data sets of data, but actually just distributing kind of black box language models. But actually, this is not also sufficient because even if it is black box, even if these language models are black boxes, actually they can memorize some data, and there are ways to extract this memorized data from language models. So there is still a possibility of data leak from language models. There are several legal regulations about health data and the use of artificial intelligence on this data. For example, in the Artificial Intelligence Act from your European Union, healthcare data is classified as high-risk data. And you may know about this GDPR, European Union regulation, where sensitive health data is categorized as special category data with special rules. And you also have regulation at US level, which IPA, ITech Act, and several other regulations in China, Canada, Latin America, and so on. And you also have ISO norms about dealing with health data, pseudonymization, and so on. So what kind of information are very sensitive in this document? This is something which is called personal identifier information. This is information such as, of course, full names, date of birth, telephone numbers, home address, and so on, social security number. So this kind of information can more or less directly identify you, but of course there are also other kind of information which can indirectly provide information to retrieve you. About your job, and different kind of information. So actually, this definition of personal identifier information is not really related to a fixed set of categories, but this is something which should be assessed case by case. Okay, so now we are going to talk about different de-identification techniques can be used. And of course, the first one is about anonymization and pseudo-anonymization, which are quite well known. So the idea of anonymization is that you can identify your personal identifiers, such as John or Paris, so names and location, address, and you can replace them by some placeholders, such as XXX or YYY. So this is a non-reversible operation. You cannot come back to your original document. And pseudonymization, for pseudonymization, you are going to replace your identifiers by some reversible tokens such as ID12 or location 24. And of course, you can keep some mapping between these tokens and the original text in such way that you can reverse the operation if you wish. So this is good, but this is not so good for data used to be to train models, because of course if you use this anonymized data to train your models, actually you are going to learn something about these placeholders or about these tokens, but this is something which breaks the flow of normal documents. And when you apply your LLMs after that on real documents, you will lose some performance. So actually, it's better to try to replace these identifiers by some pertinent replacement. For example, replace John by Paul and Paris by Lyon. And whenever possible, use a large set of possible values to get diversity, but a diversity that should be in phase with real values from a distributional point of view, I would say. So, of course, the first step for anonymization or pseudonymization is to recognize these identifiers. And these identifiers are the special kinds of name entities. And recognition of name entities is a classical NLP task. For example, to recognize names, organization, dates, address, and you see an example here of document with some name entities such as names, Barack Hussein Obama the second, dates, August 4th, 1961, and location, the United States, Illinois, and so on. I would stress out that name entity recognition is used for anonymization or pseudonymization, but of course, this is also very useful for extracting, for example, medical concepts from medical documents such as disease, symptoms, drugs, treatment, exas. And so we are coming again and again in this presentation talking about name entity recognition. So different way to do name entity recognition. Historically, the first way was to use, for example, rules with regular expression, which are very efficient. Because you may have strict formats for different kinds of expression. For example, for US secure security social number. So you have a regular expression. I'm not going to detail this expression. But of course, this kind of expression are not working so well for personal names or for addresses, for example, where for addresses, you could use, for example, a list of names, gazetteers, as you have an example here. So list of location, for example. And detection can also be helped by using not format of the entities, but actually format of the context introducing these entities. For example, in forms, you may have first names, colons, XXX, something which is going to fill the first name, last name, telephone, email, and so on. But this kind of strict formatting is very document specific. And of course, you may have errors and typos in document. You can also have some entities which is not in the expected places and so on. So rule-based names is not the best way to deal with a name entity recognition, and which is more used until recently was supervised machine learning name entity recognition, and especially using something, annotated data using this beginning inside outside annotation schema, which is illustrated here, has been the first token of an entity. So for example, Alzheimer, which will label with B, disease, so beginning entity of type disease, and then followed by several tokens, inside tokens, E disease, I disease, I disease, I disease, covers the full span of your entity. You have another one, which is a begin chemical, donazepam. And this is something which can be easily implemented using, for instance, Python library Spacey, which is doing both NLP and machine learning parts. And after that, you can complete your working flow by Python model faker, for example, which is conveniently used to replace entities by similar ones. But nowadays, of course, people are going to use LLMs. And name entity recognition can be seen as a specific task of sequence labeling using transformers, for example, BERT models. The idea is that you are providing your sentence or document as input to a BERT model, which is going to build some representation for each word of your input. And you can then project this representation of your tokens or words into labels, and you can do that directly, or you can add additional layers such as a conditional random field, for example, or bidirectional LSTM layers. I'm not going to into detail, but of course you can get better performance using this language model for doing NERs. However, I would like to mention a recent proposal which is called Gliner, which is based on different approach. The idea is that you are going to use language. You are going to build language representation of entity types. So you have entity types, for example, person, organization, or location. So this is a text. So you can build representation for this text for person. And on the other hand, you can build representation of textual spans of your input. For example, a representation for Alan Farley, for example. And then you are going to compute similarities between the representation of some type and the representation of your span. And if this similarity is above some value, about some thresholds, you are going to say, okay, I have an entity of that type for that span. So if you understand correctly, there is no need for BIO scheme for this approach. And which is also nice is that you can naturally handle nested entities, something which is more difficult to do with a BIO scheme. Also, we have done some experiments by Ryan Touchant in our team, for example, to compare Gliner with sequence labeling and using Camembert Bio. And if you observe your result, you see that we get better performance with less data with Gliner, even if at the end we get slightly better result with sequence labeling. But they are very close, and you can get a better result very quickly with Gliner, which is interesting because it means some way less annotated data for more or less same amount of result. So here we are talking about performance, and maybe it's time to tell a bit more about how we measure performance for name entity recognition. So I suppose you are you know about notion of true positive, true negative, and different kinds of errors such as false positive and false negative. Which has been used to compute precision, so how much, how well you predict true positive, and recall how many true positive you are able to collect. And this precision and recall, of course, can be used to compute F1 score and accuracy. And of course, F1 score and accuracy are important metrics, but I would like to stress out that for anonymization, actually recall is also an important metric because what you want is not to miss essential personal identifiers. So even if you are collecting entities which are not personal identifiers, this is not so an issue. Of course, if you collect many non-personal identifiers, it could be an issue, but a slightly better recall and lower precision is not so bad. And something that we can say is that rule-based approaches tend to favor precision, while machine learning and language model on the opposite tend to favor recall. And sometimes it can be interesting to combine both approaches using what is called ensembling techniques. Okay, name entity recognition followed by replacement is the first important step. But actually, when we do that, we are losing some valuable information in your document. Because sometimes we would like to preserve some information for running studies, for example, about age, sex, geographical area, job sectors, and so on. In some way, we have to find a balance between confidentiality and data utility. And for that, we can distinguish three kinds of entities. First are personal identifiers such as name, telephone numbers, emails, and of course, this kind of data should be clearly removed from document. But we have something which is called quasi-identifier. So this quasi-identifier may lead to re-identification alone, or when you combine several of these quasi-identifiers. But this quasi-identifier in some way can be partly degraded until full removal of them. And this quasi-identifier could be, for example, age, height, weight, part of social security number, because inside social security number, you are recording some demographic information, for example. And then the third kind of entities are target entities. And these target entities, you don't want to remove them or to change them. For example, this is disease in a clinical document. And we are going to exploit statistical distribution for better replacement of some of these entities, so quasi-identifier in particular. So there exist several algorithms that have been designed to do such things, particularly about when working on tabular data. So, for example, you have the notion of anonymity, where you are going to degrade precision of quasi-identifier in such a way that any combination of degraded quasi-identifier will occur at least k times in your table. But we will see that it's not enough sometimes, so you may want to use L diversity in such a way that any combination will cover at least L distinct target as attribute value. And there is something which is called T-closeness, where you want to do replacement, but as close as possible from your initial distribution over your data set. So I'm going to illustrate k-anonymity. And here you have this initial data. And some of this combination of quasi-identifier, age, sex, and city are unique. So you want to avoid that, and you want to have at least two occurrences for each combination. And a way to do that is to degrade the information about age using range of ages, so between 0 and 20 years, and between 20 and 30 years, for example. But this is sometimes not enough. For example, in this slightly different table, you can see that if you are interested in about information for some young woman from Rotterdam, you will know that she suffers from viral infection. Okay, so you can get information about this woman. A way to avoid that is to add to diversity and to degrade information. So this time about city. So removing information about Rotterdam and also Utrecht. And if you do that, you can no longer distinguish between viral infection and cancer, for example. Of course, this is for tabular data, but you can easily adapt that for textual replacement. So you collect entities from your documents. You build some data table. You apply transformation on this data table, and you inject a replace value in your documents. Okay, and the larger the data set, of course, the easier is to play with distribution and in a way that you remove less interesting information, still preserving information. However, these approaches are interesting, but they do not actually provide a rigorous mathematical evaluation of the risk. for any potential and even unforeseen attack. But there is something which is called differential privacy, which provides a nice theoretical framework for that. The idea is that you are going to use some noisy data accessor M to data, and such a way that if you consider two databases, so D1 and D2, where you have added some information about some particular person, so for example, Joe, and now you want to access data from D1 or from D2 using this noisy accessor M, well, actually, you are going to get answers which are almost indistinguishable. Almost indistinguishable means that actually the probability to observe some information O from both data set and the ratio should be below some exponential using this parameter epsilon. And this is a parameter epsilon which is providing I would say a balance between data utility and risk. So the greater epsilon is, the better confidentiality you have, but of course, the more noises you are going to introduce. It's easier to ensure lower epsilon for large databases, and of course, when you want to observe observation which are more coarse grained than fine grained. And which is interesting is that data privacy has been also declined as something which is called differentially private stochastic gradient descent, which is a way to train LLMs by adding some noises on databases. So, but I'm not going to talk more about data privacy here. Anyway, even using all these aspects, you cannot ensure zero risk when you are doing de-identification because NERS is never perfect, never 100% perfect. You can always miss some personal identifiers in your document. It's possible that it's still possible to do the re-identification using quasi identifier in your document. Maybe the degradation you have applied on these quasi identifiers is not good enough. And also something which is important, it's as NER is relatively sensitive to your document style. So you may trace a model on a set of documents, of medical document, but this model is not working so well on new data or new data set or new styles of documents. So it means that you have to do some adaptation for your new set of documents. You have to retrain, you have to transfer and adapt your model to your new data sets. Of course, you have a way to do that more quickly using pre-annotation and something called active learning, but still it's costly, it's time consuming, and so on. So maybe something which could be interesting is not use confidential data and find actually non-confidential similar data somewhere else, but where? And this is what we are going to talk in the following part of this presentation. For example, looking in public collection, but also building synthetic data. So safer data. So first approach explored by Ryan Toucher in his PhD is to find such, for example, clinical cases inside scientific papers, and you can find these scientific papers in some public scholarly collections, such as PubMed or ISTEC for French. And which is nice is that we can use LLMs to do the detection of these clinical cases, and we can also use LLMs to add more annotations that just qualify clinical cases. For example, qualify the quality of the document and also do language identification. So I would like to present this workflow, which is coming again and again, and I will talk more later in this presentation. So starting from 4 million articles from PubMed, a subset of these documents, so were annotated with a huge LLMs to get annotated paragraphs about clinical case, quality annotation, quality and language. So we get something like 400,000 annotated paragraphs. And we use this annotated paragraph to train a smaller language model, so SLM. And this SLM is much faster than your original LLM. And we can apply this SLM now to annotate 130 million paragraphs. So much more than 400 initial paragraphs, 400,000 initial paragraphs. So if we do that, we can extract something like 2 million clinical case paragraphs from our 4 million paragraphs, articles, I mean, which is something what 1.6%, which is a very low number, actually. So it's quite difficult to find this clinical case, but using the LLMs, we can do it relatively easily. Of course, we get clinical case, which are not exactly clinical reports, but again, we can use LLMs to do some reformulation of this clinical case into clinical more compliant clinical notes. And this is something, we have an example here. We see that we have, again, we can retrieve some of the expected section in a clinical report, so motif d'admission in French, something Adamez, examen clinique, paraclinique, and so on. And we can also extract some elements from this clinical case, such as sex, age, diagnosis, and so on and so on. And we can also apply these LLMs for translation. Because we have many documents in English extracted from PubMed, but actually what we are looking for are French documents. So how useful is this extracted information? Actually, we did some experiment, and the idea is that we can use this information about paragraphs to build a customized training data set for different targeting tasks. And so we can keep or remove some paragraphs from our selection of documents, and we can decide also to upsample. So, for example, sample 10 times some interesting paragraphs. And the idea is that and what we observe actually is that we get same of better performance, but with less training data. For example, if you base here correspond to using old data, so not using any kind of filtering of upsampling, but for example, for QA, for a benchmark about medical question answering, you see that something which is a data set which is more specialized on high additional quality paragraphs, we get a better result and more quickly with this customized data set. If we look at MNLU ProfMed performance, this is about understanding clinical data, and we see that a data set specialized on clinical paragraphs, so clinical case, works better than the base data set. And for French, if we focalize on French clinical data and French data extracted from PubMed, we get better performance at the base data set. Okay, so another option is to generate synthetic clinical reports using LLMs. So we did that in collaboration with Rémi Flicoteau from APHP. And so the idea is to use scenario describing some information about a patient, using some guidelines about a specific scenario, about hospitalization, chirurgy, exams, and so on, and build a prompt combining all this information, submit this prompt to Mistral. So this is a large language models, and we get clinical reports. And so if we examine these synthetic clinical reports, we can compare them to real clinical reports. For example, we can observe that somewhere these clinical reports are longer than the real ones. They use less abbreviation. They have better sectioning. And they use more vocabulary that what we can find in real clinical reports. And actually, 7 generated synthetic clinical reports were compared to 7 real clinical reports by 2 doctors. And compare about different dimensions such as language quality, coherence, medical coherence, completeness of the case, and synthesis. And what we see is that actually these synthetic reports are better written, more complete, but still we have some issue about coherence and synthesis. But they are not so far away from a real document. And they are considered as very good reports, actually. So, sorry, here is in French, but this is a sample of a fragment of such a document. And you can see this is very well written, well structured with antecedent part, mode de vie, so life mode, disease history, and so on and so on. And it's very well written. And third option, so we could say, okay, this is very nice using this LLM to generate synthetic reports, but maybe it's too far away from real documents. So a third option is to generate facsimile. So this is the work of Simon Meoni for his PhD. And so the idea here is that we are going to use real clinical reports, extract some information from this clinical report. So some keywords, UMLS keywords, for example, and use this sequence of keywords as scenario to generate document, but compare this document to this original clinical reports and use some feedback to improve the generation of reports. So this is a workflow which is shown here, where you use an initial subset or seed set of documents to initialize a generator model. And we use keywords extracted from a clinical report to generate a set of candidate reports. And we evaluate this report compared with this the real clinical reports using an evaluator model. And we get some scores that we can use to update our generator model using reinforcement learning, using DPO for reinforcement learning. And if we do that several times, so several iterations, we see an improvement of the similarity scores from generation 0 to generation 2, ranging, for example, for 67 to 72 similarity score for the first experiment. And so how we do that? So we have this original node. We extract keyword from this original node. So for example, metastatic RCC, pancreas, chill, Tylenol, and so on. And we provide this set of keywords to our prompt, and we do the generation. And we get some facsimile. So here is an example of facsimile with the high semantic score. And we can compare both nodes. Of course, they are not really similar, but they are not so far away. And relatively interesting ones, the facsimile one, I mean. But we need to evaluate how well this facsimile can replace real documents. Simon did some evaluation on a subset evaluation of this facsimile on a task where we had to predict some ICD-9 codes. So ICD-9 codes, we have many of them, so we are focused on some subset of these codes, actually the N for, most frequent ones. So N being 20, 50, 100, and 400. And here I'm presenting some result about the 100 most frequent codes. So actually, this is a what we call a multi-label, multi-classes task. And what we observe is that actually your facsimile works relatively well when compared to real data. And one of the interests of facsimile is that we, of course, can generate a larger amount of facsimiles that we have of real data. And we see an improvement of performance when we increase the amount of facsimile we are using for training. Of course, if you also upsample real data, for example, 4 times, you can get slightly better result that with your facsimile, but not so far away. We can also observe that if we select mostly the best SAM score-based facsimile, we are slightly better than when we are just using randomly sampled facsimile. And also what is interesting to observe is that actually we have a nice correlation between similarity score and F1 score for this class 100 task. Okay, so we have presented several ways to get synthetic data or public data, but I would like to mention that this the generation of synthetic data based on scenario of sequence of keywords somewhere still suffer from some re-identification issues, even if they do not leak personal identifier, because we have no personal identifier in this document, but still we have some I would say quasi-identifiers through the real sequences that could lead to potential re-identification, even if the risk is relatively low. So one way is to train on real sequences, but then generate a new data set using a purely artificial sequences not related to real sequences, but close enough from these real sequences. So to do that, we can apply some of the degradation algorithm we have seen before, anonymity or differential privacy. Another aspect is that, of course, generation is not perfect and can remove some of this actually quasi-identifier identifying. And so what we can do is to keep some of these documents with have some light default and actually discard documents which are somewhere too perfect and too close of real documents. We can build synthetic data, but we can go one step further, and actually we can use LLMs as annotator, especially on this synthetic document. So this is something we have already seen in a way with the work of Ryan on extracting clinical cases from PubMed. But this is something we can generalize, and this is a new paradigm in a way that we can take data annotated using some large language models, and then use this annotated data to train a small language models. Okay, and then we can run efficiently this small language model. However, it's not possible to send real data and sensitive real data to such large language models, either because they are remote ones and we are not allowed to send such confidential data to ChatGPT, for instance, or because you have some internal compute infrastructures which is not powerful enough to run such large language models. On the other hand, when you are considering non-sensitive data, such as synthetic data, you can submit this data to large LLMs, so ChatGPT, for example, and then you can, of course, use this annotated data to train or distill smaller models. And an interesting point is that these smaller models can be locally hosted on your medical infrastructures. But I would like to stress again that you still need some manually annotated document at some point for validation. An experiment about using LLM for annotation were done by Simon Meoni using E3C multi-liquid dataset where you have French data, for instance. So this is for name entity recognition. The dataset is organized in 3 layers. We have first layer, which is a gold layer, which has been manually annotated, and this layer is only used for validation. And you have a silver layers with weak annotation, which has been extracted using a dictionary. And a small part of this silver layers has been manually validated, so 10%. And you can already use the silver layers to train or to distill a small model, either just using your weak annotation or using both weak annotation and validated annotation. But you can also submit your silver layer to LLMs to get LLM annotations, and again, distill a small model. And you can also do some combination. So combine your LLM annotation with your validated silver annotation, or you can mix weak annotation with LLM annotation and see what you get. And you can also use directly your LLMs on your gold annotations. And then what you are going to do is to do evaluation of the result of these different annotation or distilled models against or with respect to the gold annotations. And so what we here we get some information about the number of begin and inside tokens which are retrieved by different. We are present in the gold dataset and retrieved by LLM or by dictionary. And the first observation is actually LLM again tends to overestimate, to annotate entities when compared to gold annotation or dictionary annotations. And especially we can observe that in this confusion matrix here, where we see that in Struct GPT-3, so LLM annotation, we have much more, begin and inside annotation, especially inside annotation are confused with outside annotations. And now if we run our evaluations, what we see is that we get better result. Actually, we get better. Direct evaluation with LLM annotation. Annotation provided by LLMs on the gold layer. We get a relatively good result, 74 F1 score. And if we train directly on the weak annotation, distill on silver 2, we have a much lower score, 69. If we use some subset of validated silver annotation, we are quite close from direct LLM, 73. And now if we are using LLM annotations, we are as good as so we have distilled a small language model, and we are evaluating this small language model, and we see that actually this small language model is as good as using directly our LLM on the gold layers, 74 F1 score. And if we mix weak annotations and LLM annotation, we can get even better 76 F1 score. And we see on the other side of the slide that we can find the best mix, which is somewhere around 0.5, so equal mix of weak annotation and LLM annotation to get the best distilled models at the end. Okay. So conclusion is that LLM annotation may be of good quality, and something which is interesting with when you distill a small language model is that they can be as good as a direct use of LLMs, and sometimes even better because in a way they are doing some kind of regularization on your set of annotations. And also that is interesting to combine, it may be interesting to combine several annotation techniques, so ensembling, and also that can still be interesting to use a small amount of validated annotation in your distillation. Coming back to our synthetic clinical reports, which has been generated using LLMs, actually, we use also LLMs to generate annotation for this generated clinical notes about entities, but also about ICD-10 codes. So we have 20 categories of entities, and we had something like 26,000 entities in our set of documents. Okay. I'm not going to go into to enter into the detail of the distribution of different kinds of entity and codes, but of course this is not very well balanced between the different categories and codes, as usual. And so here, that's the kind of annotation we get. So a fragment of our generated nodes. So about, and we see that there is some errors, or maybe it's me when I did the find. It's been Lucien Cornuche sex is not the right one. Age for 61, and you have different kinds of entities which has been detected by LLMs. And we use Gliner to fine-tune some Gliner models. Actually, we use the data to fine-tune some Gliner models and run some evaluations, and with relatively promising scores. But of course, now we need some evaluation on real documents, not synthetic clinical notes, but and not just real document, but real document manually annotated, or annotation manually validated at least. So this is something yet to be done. Okay. And to conclude, I would like to come back to clinical models. Because we know there are some foundation models such as GPT, Close, Llama, Mistral, DeepSeq, more and more every day. And some of these models, as you have seen, are oriented for biomedical data, I would say. But there is still a need for more specialized clinical language model trained on on realistic, I would say, clinical data. And also for other languages, that English in particular, for French in my case, because somewhere we need in these LLMs to capture some, I would say, cultural background. This means the way French medical documents can be different from I would say, American medical documents. In particular, but because maybe this is not exactly the same best practice in the US and France, and so on and so on. And so the best way to reach that goal is to train a model from scratch with a very large amount of biomedical data set and clinical data set. But we know that it's costly in terms of compute to train such language model from scratch, and it's also difficult to collect a large amount of data. We can try to continue the training on some existing model. So this is called continual pre-training. And in that case, we can use smaller data set. And it's also possible, because it's smaller data set, to use some data set which has been distilled or extracted from used LLMs, such in a way that we have seen before, for instance. So I would like to talk a bit more about Camembert Bio, which is a specialized biomedical small language model derived from Camembert, and this is a work done by Rian Touchin. And this Camembert Bio is already largely used actually in the French medical community. And so to train this version of Camembert, we use a relatively small data set of public data extracted from public sources, such as ISTEC, CLEAR, I3C. So only 400 million documents, I think it's document. So a new version of Camembert Bio has been distributed this year. So Camembert Bio is already a useful French biomedical small language model, but we cannot really say this is a true clinical LLMs because it was not trained on real clinical notes, for example. Still, if we do some evaluation of Camembert Bio on the NER task, for example, we see that Camembert Bio work better than Camembert base, so without any continual pre-training on medical data. On different kind of benchmark, so clinical oriented name entity recognition, scientific NER on scientific document and NER on leaflets, medical, I mean drug description, for example, EMEA. Sorry. And here, this is an evaluation done by other people, Medialogue FR. So the paper by Liu and all in 2024. So here it's not NER task, but a multi-level classification task. And here, Camembert Bio has been compared to other proposition, other model for French, in particular Dr. Bert, which is also a kind of medical small language model for French. And you see that Camembert Bio has a good performance, the best performance actually on this task. There are other tasks that could have been present, but I have no time for that. And I would like to conclude on the ongoing project, which is called French Gen for Health, so FG4H, where the idea is to collect public medical data, as we have seen before, so PubMed and so on, ISTEC, but also a very large set of real medical clinical data, which is going to be pseudonymized and hosted on some secure infrastructure. And we are going to use this data to continue the pre-training on two models. First one, which has been open source language models, which is going to be freely available, and something which is called a community language model, trained on this confidential clinical notes, which will be available only on the accreditation for remote access, or maybe it could be also downloaded for some further fine-tuning, but downloaded only after some condition has been satisfied by the people who wanted to get this model. Okay, so in conclusion, I would say from personal experience that working with real clinical data set remains very difficult and of course still dangerous because of this risk of data leak and because we have still never a zero risk about confidentiality, and we are very constrained by legal regulation about using this kind of data. And also that, of course, the more real data we are using, the more risk we get of leak, for example. And we know that large data sets are actually used to needed to train language models. So I would say that synthetic data and public data seems interesting options to create a more open data set. Because there are ways to increase the volume of data we can use. So I mean, generating more synthetic data, for example. And of course, that with this synthetic data, we can use large compute infrastructure, such as Zanzé in France. And we can also use LLMs to annotate our documents, synthetic data and public data. We can transform them, translate, for example, do some summaries, many kind of transformation we can try. But of course, with this synthetic data, but also public data, there is a risk of lack of diversity and some important differences between these documents and real documents. So facsimile is maybe, with feedback from real document, is maybe a better option because we can access a greater diversity of scenarios which are in core in reality. We have better adequacy, of course, with real document, and this facsimile may better act as proxies for real documents. but still we have some risk of re-identification because of this scenario extracted from real documents. But in a way, the larger data set this time, the lower the risk instead of the greater the risk. And the more possibilities we get to play with distribution using the different algorithms I've presented, such as anonymity, differential privacy, and so on. Okay, and that's the end of this presentation. So I thank you for your attention and open for any question of your part.
Thank you very much for this in-depth presentation, Mr. de Clergerie. It was very, very interesting. And we have some questions from the attendants. Some of
Okay.
them you have already answered, but maybe you will like also to add some things. The first one is regarding anonymization. Is there a possibility of anonymizing data through Python based on an Excel file?
In a way, yes, because it's relatively easy, for example, with Pandas, which is a Python framework, to extract the data from Excel files, to build data frames from Excel files, and say once you get these Panda data frames, you can apply the techniques presented today. So, I mean, do your replacement, anonymization, k-anonymization, L-diversity, anything you want. And then you can reverse the process. I mean, you can export your Panda data frames back to some Excel data sheet. So this is kind of things I've done because I'm a researcher at INRIA, but I've also worked sometimes in industry and working with people using Excel files. So that's the kind of things I have to do. I mean, importing from Excel files and then exporting back to Excel files. And so it's absolutely possible to do that with Python. And when you are in Python, you can apply the kind of tools I've been presenting today, such as Spacey, Faker, and other modules, of course.
Okay. The next question you have already answered, but maybe you would like to add something, is about the difference between SLM and LLM. The question was, why is an SLM considered better than an LLM? I think mainly you already answered to this question, but maybe you want add something.
Yeah, I can complete that because that's somewhere that important point. We are talking a lot about large language models, LLMs, but LLMs are covering actually a large range of size, ranging from something which a few hundred million parameters to 1 trillion parameters, for instance. And this is absolutely not the same thing when you are talking about 100 million parameters and 1 trillion billion parameters. For very large language models, you can only use remote access, and they are costly to use, and so on and so on. You cannot use them when they are remote access. You cannot use them for submitting confidential information. This is absolutely forbidden to do that. But when we are dealing with language model, something like a few hundred million parameters or a few billion parameters, I would say 1 billion parameter, 4 billion parameter, even 8 million parameter, they may be considered as small language model, SLM. So this is something we are more and more talking about. This notion is present in the literature, small language model. And you have many interests in these small language models. They are more frugal, less costly in terms of energy, which is something which is important when you use these models in production. And they run faster. They can be hosted inside your secure infrastructure. You don't need remote access. So they are particularly well adapted for medical processing, I would say.
Okay. And the next question is also related to this almost. It can be related also. The question was, when resources are scarce and you cannot host big LLMs on premise, is
Yes.
there a safe way to anonymize medical data for it to be safely transferred into an LLM API provider? So,
well, that's the idea of a small language model. They have to be small enough to be hosted where the real data are present, that you can use these small models for anonymization, and then you can send your anonymized document to some remote place where you can apply larger LLMs on them. But still, you need to be able to run this anonymization process on premise where you are, where the data is. So small language model, or if not possible, a lighter option such as machine learning models. Maybe it's enough for that. But I would like to recall that even anonymized or pseudonymized data is still considered as sensible data. You cannot do anything, even if you have done some anonymization or pseudonymization, you cannot freely distribute this data or send it over non-secure channels and so on and so on. So you have to take extra cares even with this pseudonymized data.
okay, thank you. The next question is about, what about Gemma model? I don't know about it, but maybe you.
Yeah, it's a variant of Gemma models. I'm not sure. I think it's Google models, Gemma models. And so it has been specialized for medical data. So kind of things we are proposing for FG4H. So they have done some specialization using additional medical data. So this is a relatively good model for processing medical data. It's one of them we are using. But have you seen there are others? For example, Mistral is relatively good for generating French medical data. So we have used it for generating this synthetic clinical report. But actually, Rian has done also a further experiment generating synthetic clinical report with other medical models, and MedGemma was one of them. We also used some of Yama models, and other ones. I don't remind which one, but the third one. And for all these models, we got a relatively good clinical report also for French.
Okay. The last question was about, is more technical, I think. What are the most effective and scientifically validated approaches to addressing VPN-related challenges, such as secure remote data access, authentications, and compliance when handling sensitive medical data in a large-scale healthcare system? But
yeah.
it's more related to cybersecurity and things like that.
Yeah, that's what I wanted to say. I'm not really specialized on these issues. You have this notion of HDS certification, for example, about storage and access to secure data, which is something you have to take into account when dealing with medical data. But I have not the detail of all these conditions which are expected for HDS certification. But yes, the first point is use VPN. That's clearly a first step. But it's more than that. It's not just getting a VPN with some, I would say, dynamic codes for accessing also, not just password. And of course, clear separation of networks between inside of your system and outside. So a strict barrier and so on and so on. But I cannot done all details. I'm the specialist on these issues. But that's quite important when you are dealing with medical data, of course.
Okay, thank you very much again, Mr. de la Clergerie. It was a very in-depth presentation. I think it was the